Hello, am I audible?
Yes, yes, audible. Good
Yeah,
evening.
good evening. Yeah. Okay, yes. Okay, welcome to week five's problem solving session. Today, what we'll do first is solve some of the problems from last year's week five assignment. Then, as one of you asked, we'll take a brief look at diagonalization after completing this week five assignment. And if we have some time, then we would also solve this year's week four assignment. Okay, yeah. So let's start. Yeah. So the first problem is, suppose there is a randomized algorithm A which accepts X when X is in L with probability 0.7, and it rejects X when X is not in L with probability 1. Consider the algorithm double A, which does the following. It runs A two times on the input with independent random coins, and we accept if any one of the runs accept and reject otherwise. So what is the probability that double A accepts X if X is in L? Just again some question. Okay. So would anyone of you like to guess the answer to this question? Because this needs to be worked out. Okay. Okay. So okay, can I, at least can you okay, so one of you are saying 0.49. I don't think it would be 0.49, it would be at least more than 0.7. Okay, so can you tell me why you thought it was zero point 0.9? Like what approach did you try? Okay, 0.81 might be possible. We'll have to see. Yeah. So at least can you tell me what approach like led you to these two numbers?
Yeah, just a moment.
Yeah.
So, am I audible?
Yeah, yeah.
So, first I thought that the probability of acceptance would be simply multiplied with itself, but we have to like look at the probability by which it would not be accepted. So,
Okay.
like with probability 0.3, if X
Right.
belongs to L, it would not be accepted.
Okay.
And if we run twice, so with probability 0.09, just squaring it, it would not be accepted if X still belongs in L.
Okay.
So 1 minus 0.09, which I
That
think
is 0.91, right?
0.91. Sorry, I typed it wrong,
Yeah.
but I had that in mind.
Yeah. Okay. Yeah. So that's one way to do that. Uh, so what I'm going to do is mostly similar, but it's yeah, it's mostly similar. Okay. So probability that AA accepts. Okay. Is equal to probability AA accepts X. Okay. Instead of writing it accepts in the first, let me just write this. First run accepts X plus probability. Okay, so what should I write over here? So okay, what I want to do is I want to say that okay, A accepts X if the first run accepts X and something else. So what should I write over here?
so first one is a failure and the second one is an
Right.
acceptance.
Yeah, so this is why I'm doing it like this. So you can't just write second run accepts because the first run accepting and second run accepting are not disjoint events. So if you want to add
Yes.
probabilities, your events have to be disjoint. And to do that, you need to do this. And second run accepts. Okay, so now this is as it is. Yeah, so I'll keep the first quantity as it is. For second quantity, I can write this, right? probability second run accepts, given first run rejects, times probability that first run rejects. And so since I'm using conditional probability over here, so far I have not used the fact that both runs are independent. Okay, this would have been true even if the runs were not independent. Or rather, if I had we hadn't been using independent random bits in both runs. And okay, again, this stays as it is. Okay, now my claim is that I can write just this. Okay, so why can I change this entire thing to just this?
Because these are independent events. The
Right. So
second
yeah, we are
accepts.
using independent random bits in both runs. So conditional probability is the same as the actual probability. And so then this is just 0.7 plus 0.7 times 0.3. Yeah, 9. Yeah, so this is one way to do it. Another way is to just say that, okay, A accepts it, except and only if uh, that probability is 1 minus A rejects X, and then what you can do what you suggested. Yeah, so this is fine. Yeah, okay, so then let's look at the next problem. Now, the next problem is consider a randomized algorithm A for a language L which accepts X when X is in L with probability 0.7 and it rejects X when X is not in L with probability 0.8. So with respect to the algorithm A, what can we say about L? So which class can we say that L is in? And we are supposed to select all the correct options. The options are RP, ORP, ZPP, and BPP. So with respect to algorithm A, which of these classes contain L? Okay, that D is correct. Okay, so why can you rule out, since we are supposed to select all options that are correct, can you first tell me why can we rule out A, B, and C?
Because RP is one-sided, and same is true
Right.
for the co-RP, which is also
Yes.
one-sided. And in case of the JPP, we do not know kind of the conditions, and which is not the case here. So clearly, only BPP is remaining.
Okay, so what did you say for ZPP? I didn't hear that properly.
So for the ZPP, we are sure. I mean, we are not going to make any mistake,
Okay.
uh, because we have been given don't know conditions also. So therefore, ZPP is not true either, resulting
Okay,
into
that's right.
only the
That's
BPP.
that's one way to show that ZPP is not. Like this is not a ZPP. Another way is to show is that ZPP equals RP intersection co-RP. Since it's not in RP, it's not in co-RP, it can't be in ZPP.
Yes, yes,
Yeah.
yes.
And okay, so but why is this in BPP? Oh, you need not raise your hand. You can directly unmute yourself and ask.
Okay, so
Yeah.
I had just one thing to ask here. It says that it accepts when it is in the language with probability 0.7 and it
Right.
rejects with probability 0.8 when it is not there. So,
Hmm.
like in the lectures, we have mostly seen that the probability for acceptance is usually greater than the probability by which we
Yeah.
reject. So,
That's
does
what I
this?
was coming to.
Okay.
So yeah. Okay. So as you pointed out, the next question is this. So in the lecture, you saw that the probability of acceptance While BPP is like 2 over 3, and this should be, it rejects when, so both of these should be 2 over 3, right?
Yes, something like we expect a gap between the probabilities, I think. We had like it should be at least half plus 1 over polynomial, and the
Okay,
probability for rejecting should be half, and there should be some gap, like it can't be same as in the case of, I think it was PP, class PP.
okay, yeah,
Uh,
okay, so what you saw in class was this, right? Probability, okay, X is in L
so I
implies,
have something to say here,
yeah,
that yeah, probably in the lecture, that if a string is not the part of the language, then the probability of its acceptance was less than 1 by 3. So
okay,
which makes that if X is not the part of the language, then the probability of rejection would again be higher than two-third. So in case of the
right,
BPP would be having the higher probability of for the strings which are the part of the language, and the higher probability of the rejection for those strings which are not the part of the
yes,
language.
that is true.
Yes. So even though there is a gap in the BPP, but then valid strings are getting accepted with the higher probability, and the non-valid strings are getting rejected again with the higher probability.
Yeah,
So, but then how does it contradict with? I mean, with this question, even though there is a gap in the BPP, but then it does not contradict with the statement of the
yeah,
problem.
it doesn't. Yeah, that's what I'm saying right now. Okay. So what you saw in class with this, X is in M implies MX equals to 1. That is MX. Okay, let me write except because there is except over here. Or okay, M accepts X. This is greater than 2, 3, 2 over third, right? Which is roughly 0.66. So yeah, this is satisfied. And X not in L implies probability M accepts X. Uh, is less than equals to 1/3, and this implies that, yeah, okay, yeah, I'm writing. Okay, so this is what we get, right?
Yes.
Yeah, and okay, so now if you compare both the probabilities, when X is in L with probability 0. Okay, which accepts X when X is in L with probability 0.7, which is greater than this, right? So that is fine. It rejects X when X is not in L with probability 0.8, which is also greater than this, so it is fine, right?
Yes.
Yeah. Okay, one more okay question. Suppose this probability instead of being 0.8 was 0.008. What would have happened then?
So now the probability of rejection is pretty low.
Hmm.
In the case when the string is not the part of the
Right?
language. So then this will not be the case of the BPP.
Okay, it would still be in BPP because you can
Mhm.
always boost the probability, right?
Yes, but then I'll have to conduct the experiment multiple times.
Yeah. But yeah, since the algorithm is like it's polytime, it would be fine, right? The final algorithm would still be polytime.
Yes.
So basically, you can replace this 1 over 3 by 1 over 2 plus inverse poly n in both cases, here and here as well.
Yes. Yes.
Yeah, but this poly gap is necessary. So that is, so okay, that's what we mean when we say that there is a gap in BPP, but no gap in PP. So in PP is just this, strictly half, greater than half. Over here it's half plus 1 over poly n.
Can you explain this polycap? Uh, what this poly of n here is?
Okay, poly of n is any polynomial function of n. So it's like n to the k for any k. For okay, some fixed k, which is
Okay.
constant.
Yes, I understood.
Yeah. Okay, so sometimes we use this notation. So both of these are the same.
Yes.
Yeah, but just to avoid writing this thing in the power, we sometimes use poly n.
So when I write 1 by 2 plus 1 by the poly of n, I mean to say 1 by 2 plus 1 by 3 or 1 by 4.
No, no, 1
All,
by 2 plus 1 over n to the 3 or n to the 4.
okay, so how will you justify the 1 over the Pn here in the in this example?
Okay,
Let
so,
the
okay. So let me write it. Yeah, so the probability should be greater than 1 over 2 plus 1 over poly n, right? Now, in this question, I can put no, this next question. Okay, so put okay, uh, 1 over 2. Okay, what is this difference? 2 over 3 minus 1 over 2 is equal to 4 minus 3 over 6, 1 over 6. Is also okay, 1 over 6 and 6 is poly n. So this function can grow as, okay, this function can be as large as poly n. Okay, so it's n to the order 1. I can put a constant that's still n to the order 1.
yes, yes, yeah, I understood.
Yeah,
Yeah, right. It could be a constant. That
yeah.
is
So
what I said.
basically, yeah. So basically, this can grow, can be as large as a polynomial function in n. It cannot be larger. So for example, this function cannot be 2 to the n or can't even be log to the log. Yeah,
So this poly of n could be a pretty large number, like say it could be 1 million or 1 billion also.
yeah. Okay. My point was it doesn't even have to be a number. It can even be n to the 1 million, where
Yes,
n is the input size. N to the 1 million is much larger than just 1 million, right?
yes. So
Yeah,
it can be a pretty large constant. That is also possible.
yeah. That is also possible.
Okay, yes, I understood. Yeah, fine.
Yeah, but the larger this is, the more time you would have to repeat to boost the probability to 2 or 3. Yeah.
Mhm.
Yeah.
Yes.
Okay,
Uh,
so this is, yeah.
just one more thing. You replaced zero point 0.8 with 0.0088 at one instance, right?
Oh, yeah.
Yeah. So what was the conclusion for that? Like, would BBP still hold?
Yeah. It would still be in BPP because
Oh,
0.008 is just a constant away from 2 over 3, right?
yes, but zero point
Yeah.
zero zero 0.008 is like much smaller than, so that would mean that we would have to repeat much more times
I think,
to.
okay, since it's just a constant away from half,
Mhm.
you would only have to repeat constantly many times.
Okay, but relatively, like when it is zero point 0.8 and when it is
Oh, so when it's
0.00,
0.8, we don't need to repeat at all, right?
yes, yes.
Right.
But if we like lower it to say 1,000 times, so we would have to repeat a much, like say for 1,000 times more or something like that. Would that be a case?
I think you would have to repeat roughly log 1,000 times more.
Okay, so
Yeah,
just one.
roughly.
Okay.
Yeah, I think. Yeah, but I might be wrong. You will have to like look at the exact Chernoff count.
Yeah, but we can
Yeah.
just say that repetitions would be more. Like,
Yeah.
yeah, that
Yes.
would be true, right?
Yeah.
Yeah.
Okay. So is this fine? Yeah. Okay. So then let's look at the next problem. So the next problem is consider the following algorithm for 3-SAT on n variables with probability half. Set each variable to 0 or 1. If this assignment satisfies the 3-SAT formula, then output satisfiable, else output not satisfiable. Which of the following is or are correct? Let me move it here. Yeah. The algorithm is always correct. The algorithm runs in polynomial time. The algorithm may give false negatives but never false positives. The algorithm may give false positives but never give false negatives. And the algorithm may give false positives as well as false negatives. So which of these are correct? Okay, someone mentioned B and C. Okay, yeah, the algorithm runs in polynomial time. That is correct. And the algorithm may give false negatives but never false positives. Yeah, that is also true. Okay, so is it clear to everyone that the algorithm runs in polynomial time?
Yes.
Yeah.
Yes.
Okay, so and why does it give false negatives but not false positives? So can you first give me an example, or can you first tell me why it can give false negatives and then why it can't give false positives?
So finally, the Boolean expression will come out to be true only if it is a satisfiable assignment. So
Okay,
it can never result into a false positive.
right. So if a formula is not satisfiable,
Ah,
there is no way this algorithm is going to find a satisfying assignment. Yeah, so it
yes,
can never report false positives. That is true.
yes, yes. However, if a wrong assignment is given,
Hmm.
so then quite possible that a formula, despite being a satisfiable formula, I mean, we may
Yeah,
get a non-satisfiable assignment. So it may give
right.
false negative.
Yeah, so consider a case in which the formula has only one satisfying assignment. And since you pick an assignment randomly, with very large probability, you won't pick the correct assignment, right? So in
Yes,
that
and that
case,
probability will
yeah,
be one by two raised to the power n.
what would be 1 by 2 raised to power? The probability of
Say,
success.
yes, yes, yes.
Yeah,
If only one assignment is true, then
yeah, yeah. So false negatives are possible, and in fact, most of the time, this algorithm would give you false negatives. So is this fine?
yes.
Yeah. Okay, so let's look at the next problem. The algorithm in the next problem is similar. There is just some slight change. So consider the following algorithm for 3 sat on n variables. With probability half, set each variable to 0 or 1. If this assignment satisfies the 3-set formula, then output satisfiable. Else, repeat the above by picking another random assignment. Which of the following is or are correct? The algorithm is always correct. The algorithm runs in polynomial time. The algorithm may give false negatives but never false positives. The algorithm may give false positives but never false negatives. And the algorithm may give false positives as well as false negatives. So which of these are correct? Yeah, A is correct. Okay. And the reason that this algorithm would always give you a correct answer is, okay, suppose the formula were satisfiable, then it would pick an assignment. If that assignment does not satisfy the formula, it would pick another assignment, right? And it would keep on doing this randomly till it exhausts, like till it figure out the right assignment, right? So if the formula is in the language, this would eventually find it, find the right assignment. And if the formula is not in 3-sat, then no matter how many times this would try, this would never find an assignment, right? So the algorithm would always be correct.
Yes.
But what about polynomial time,
So for each variable, for each literal, we have two possibilities. Say and we keep on repeating this experiment.
right?
So in total, we'll have to exhaust 2 raised to the power n number of the possibilities.
In
If
the
only
worst
one.
case, yes.
Yes.
Yeah. So this algorithm need not run in polynomial time. And in fact, it won't run in polynomial time. And for the and since like A is true, B, C, and D cannot be true. Because yeah, if it's correct, you can't don't have false positives or false negatives, right?
Yes.
Yeah. So the only correct option over here is A. Okay.
Uh, just
Yeah.
one thing for this algorithm,
Mhm.
the probability of error should be 0,
Yeah. Yeah.
right?
Okay. Okay. The probability of error is 0 because this is sort of a ZTP type algorithm, right?
Yes.
It keeps on trying until it succeeds.
Okay. So what I want to say that like for this one, the probability of error is 0 and the number of repetitions is 2 raised to the power n in the worst case. Can
Yes.
you say
Okay.
that?
There is just one technicality. That number is in expectation.
No, I'm not talking about ZPP. I had just like I am not keeping ZPP in the context, like
Okay.
something different. So like first time in the lectures when boosting was discussed, so we were trying to bring down the error to a constant, say 1/4 something time.
Okay,
So
right.
the number of repetitions came out to be 2 raised to the power n multiplied by natural log of 4.
Okay.
So the number of repetitions exceeded 2 raised to the power n. What I mean to say in that case,
Okay.
when we are trying to bring down error to 1/4, which is still like positive, right? So
Okay.
was that the case because we were not doing this, we may be picking some assignment more than once?
Yes, that is true. And also another reason is like you have no reason to believe that all of the inequalities used were typed, right?
Sorry.
So the way you would have done that was through a series of inequalities, right?
Yes.
So you had like the running time of the algorithm and then less than equals to a bunch of inequalities, right?
Right.
Those might not be typed.
Okay.
So just because you get something like the running time of the algorithm is at most say 2 to the n times log 1 log 4
Right.
does not mean that the running time of the algorithm would be exactly that, right? That's just an upper bound.
No, like that was the number of repetitions, like approximate number of repetitions we needed to bring down the error to 1/4, say.
Right. So what I'm saying is, was there an equality over there, or was there less than equals to sign? So was the statement
No,
this? The number of
there was.
repetitions equals to this, or the number of repetitions less than equals to this number?
So we used just an approximation where we like did 1 minus 1 over x raised to power x and limit extending to infinity. We
Okay,
like
then
used
yeah,
that.
so that would give you a less than equals to.
Okay, less
So
than
you can
equals.
replace that approx by less than equals to.
Okay, so that still holds then, right? Okay.
Yeah. So in a lot of cases, like you won't get the exact number, you would get an upper bound or a lower bound, but that would be enough in our case.
So what I was thinking, like maybe that extra one is coming due to picking same assignment more than once, because that was
Right.
not a
Okay.
condition there.
Yes. So
So
that's one of the reasons. And
okay,
another could be that some of the inequalities were loose.
okay.
Yeah. Okay. So the next problem is, it's also about a similar algorithm for 3-stat. Consider the following algorithm for 3-stat on n variables with probability half, set each variable to 0 or 1. If this assignment satisfies the 3-set formula, then output satisfiable, as else output not satisfiable. Then out of the following options, select the tightest upper bound for the probability of error of this algorithm. 1 minus 1 over 2 and 1 over 2 and 1 minus 1 over n and 1 over n. So which of this is the tightest upper bound on the error probability? Yeah, yeah, it's A. So can you like tell me why is it A?
Yes, so in the worst case scenario, there could be one satisfiable assignment. So the
Okay,
chances are 1 by 2 raised to the power n. So the in the worst case scenario, the the error, the chances of the
right.
error would be 1 minus 1 by 2 raised to the power.
Okay, yeah, but that just treats one case, right? What about when phi is not in 3-sat?
So I could not hear. What happens when pi is not?
Okay, so we want to find an upper bound on the error probability, right? So we need to
Yes.
do two things. Number one, when phi is in 3-sat, with what probability does it get rejected? We need to upper bound that. And when phi is not in 3-sat, with what probability does it get accepted? We also need to upper bound that, right?
Can this ever happen? That
Yeah,
uh,
that's the point. So when phi is not in 3-sat, phi is rejected. This is one, right?
yes.
Yeah. So the case is that this is the case of one-sided error, and so what you told holds, right? Let me just write it. Okay. So probability that I is accepted is the same as the probability that uh, the assignment, the random assignment, is a satisfying assignment. And this is at least 1 over 2 to the n, right?
Yes.
So yeah. Yeah, so the okay, but this is just one upper bound. Why is this tight? So the question is, select the tightest upper bound. So we need to show that there is a case in which this upper bound will have occur. Why is that true?
So this is the tightest one only. I mean, can we found better than this?
Okay, so that's what we have to argue that we can't, right? So okay, when can you say that this is tight? If you can find an instance, so that if you can find a phi in 3SAT for which your algorithm should take 1 over, like, should reject with probability at 1 minus 1 over 2 the n. Okay,
Mhm.
so can you think of such a formula?
Could you please repeat the
Okay,
statement?
so over here we have that this probability is at most this, right? But since there is a less than or equals to, it might be possible that this probability is just half. Okay, if we want to prove that this is the tightest upper bound, what we need to do is we need to show that there exists a phi for which this is an equality. That so there exists a phi for which the rejection probability is exactly this. So my question is, can you think of such a phi? Okay, so when will the probability of rejection be exactly this? That is the
Uh,
same as saying when will the probability of acceptance be at most this?
So
yes.
a 5 with only one satisfying assignment.
Right, and yeah, so when phi probability phi is rejected, so the bound is flat. And one example of such a phi is, like, can you give me one any example, a trivial example?
And of
Yeah.
all variables.
So this is only one satisfying assignment, everything is one. Yeah, so not only is 1 minus 1 over 2 to the n 2 to the n an upper bound, it's a tight upper bound. Okay, is this fine? Yeah.
Yes.
Okay, so then let's look at the next problem. The next problem is, if a language belongs to the class RP, then it also belongs to the class ORP, true or false? And yeah, before you answer, I think you should interpret this as, is it currently known to be true or not? Yeah, so which of this is true as per current knowledge? Yeah, as per current knowledge, this is, I mean, we don't know whether this is true or not. Yeah. So then let's look at the next problem. So the next problem is if P equals to RP, then which of the following statements is or are true? P is equal to BPP, P is equal to co-RP, P is equal to ZPP, and ZPP equals to BPP. So which of these are true? Yeah, it's B and C. Okay, first, why can't we say anything about A and D?
Uh, because like we can say that RP contains P and BPP contains RP itself. So
Okay,
the equality we are considering about is entirely contained inside BPP.
right.
So like just
Or okay,
nowadays
might
we
be
cannot
entirely
say.
contained might be entirely contained inside BPP because right now P versus BPP is an open problem, right?
Yeah, yeah, we are only assuming
Yeah.
that RP equals to RP, that everything else is
Yes. Right.
like an
So
open problem. Right?
yeah.
And similarly, we can't also say anything about the fourth option.
Yes. Okay. So okay. So A and D are completely ruled out. So why is B true now?
So P is equals to ZPP, we can say, because P is like entirely contained in ZPP, and which is entirely
Okay.
contained in RP.
Okay. So we are talking about C first. Yeah, that is true.
Yeah, I'm saying that. So if we like, it is something like P is contained in ZPP, which is contained in RP. So if I'm
Okay.
saying
Right.
that first and third are equal, so ZPP should also be equal to both of them.
Yes. Okay. So this P is contained in ZPP. This is contained in RP, which is equal to P, and this implies P equals to ZPP. And what about option B?
So for option B, I think we can use the like the thing that P is what do we say, that it is under complementation,
It's closed in complement.
closed under complementation. So
Yeah,
that we can use.
yeah. So basically, it's this P equals to okay. Not let me not write P equals to OP. Let me not write this. So if L is in co-RP, then this means that L complement is in RP, which means L is in P. Sorry, L complement is in P, which means L is in P. Here we are using the fact that P is closed under complement. Since L is in P and P equals to RP, L is in RP, and so ORP is contained in RP. And like as we have seen a lot of times, whenever O of something is contained in that class, the reverse also holds, right? The RP is contained in co-RP. So co-RP equals RP equals P. Yeah. So this is fine. Yeah.
Yes, but it is very difficult to remember the relation in between the normal complexity classes and the probabilistic complexity classes. So, is there a shortcut to remember these relationships? Like at this point, I could think of that in the case of P, there would be a single branch, and in the case of the RP, it would be an entire tree wherein some of the paths would be leading to the acceptance and the number of those paths would be greater than say half. So
Okay.
since P is a single branch of the tree and this RP and co-RP, all these are the trees. So clearly P would be the subset of the RP as well as a subset of the co-RP.
Mhm.
So I could think in this way. So is there a shortcut to remember these relations?
Okay, so basically P is containing all the classes you are looking at. P is containing ZPP, co-RP, RP, BPP.
Yes.
And
And
yeah, So the only other thing that you need to worry about is the relationship between NP, BPP, and RP, right?
Yes.
Okay, so okay, what happens in RP? If X is in the language, then there exists a path which leads to accept, right?
Yes.
So at least
There.
half of the paths lead to accept, right?
Yes. Yes.
But that means that there exists a path which leads to accept, right?
Hmm.
Okay, and that is the condition for NP, right?
So that path can be used as a witness. So yes.
Yes.
Hmm.
And when X is not in the language, all paths reject. So there is no path that you can use as witness, right?
Yes.
So that would tell you that RP is contained in co-NP.
RP is contained in co-NP.
Because if a language is in a, RP, then
Hmm.
X and X belongs to the language, you have a path which you can use as a witness. If X is not in the language, there is no path which you can use as a witness, right? So that is exactly what NP requires, right?
Yes.
So
Yes.
being in RP implies being in NP. So RP is contained inside NP.
Right. Right.
Yeah. And okay, so then you can, so yes, then by like just taking complements everywhere, you can show that co-RP is contained in co-NP.
Okay. Okay.
Right.
And then BPP is the intersection of the this.
Oh no, that is ZPP, right? ZPP is the intersection of co-RP and RP.
Okay. Okay. Okay.
Yeah, so ZPP is also contained inside NP.
Uh, yes. Yes. Now I understood. Yeah.
Yeah.
Just one thing to mention. RP is contained in NP, co-RP is contained in co-NP.
Yes.
Right?
Yes. And
Uh,
the BPP is the intersection of RP and then
ZPP.
BPP.
No, no, BPP
yes.
is not the intersection of RP and co-RP. BPP contains both. Okay, so okay, let
BPP.
me write, right? Okay, let me write all the relations down.
Yes.
Should
P
we
is
better
contained.
draw a Venn diagram, something like that?
Okay, let me try. I don't
I
think
have
I'll
a
be able to
picture.
draw
If
much.
I think if I may share, it is like bit
Yeah.
comprehensive.
Okay,
How
yeah,
should
then you
I
can
say?
share it. That would be great because I don't think I'll be able to draw it. I'm terrible at drawing.
So where would I share it? Like, just let me try. Should I share my screen or something else?
Also,
What
if
should
it's a PNG, you can like put in the message. I think it should work. Okay.
Okay, just give me a minute. I'll share you the link itself, right?
Oh
So
yeah,
you
that
can,
would be. Yeah.
right.
So in the meantime, I can.
Okay, I've sent it in the chat.
Oh, so this is our intersection core.
But this is huge diagram. This is so very difficult to understand. Even yeah.
Yeah, but it covers everything. So
Yes. Yes. It
Yeah.
covers.
So
Okay.
it does not have BPP, but yeah, BPP also does not. Okay, over
yeah,
it does have. Yeah,
BP
yeah.
BP is
Yeah,
there.
it's written. Yeah. Uh,
BPP. Yes. BPP is here. Yes.
yeah.
Right.
So yeah, and this is yeah. So it's ZPP that is the intersection of RP and co-RP, not BPP. In fact, it's this RP and co-RP are both contained in BPP. Okay. Also, like we don't know anything about BPP, but okay, yeah, I should also write that. BPP versus NP. Okay, BPP versus NP. BPP versus ORP. Oh, sorry, CoNP. BPP. versus P are open equals. Yeah.
For BPP versus P, isn't like P a subset of BPP?
Oh yeah, I should also write that. Yeah.
For
Let me
this
write
question, why we didn't take that A option?
which is
Why it is not satisfy A
yeah.
option?
So what was oh, P equals BPP. Okay, so from P equals RP, can you say anything about P equals BPP? So RP is contained in BPP, right? So just because P equals RP doesn't necessarily mean that P equals BPP, right? Because it is possible that there is a language in BPP that is not in RP, right?
Okay.
Yeah. Basically, we have this relation, right? And it is possible that this is script. So it's possible that this is script, is right? Yeah, but if this were P, if the question were P equals BPP, then it would be equal to BPP, ZPP, RPP, co-RP, everything. But yeah, it's RP, so you can't say anything about BPP. Is this fine?
Okay.
Yeah. Okay, so if this is fine, then let's look at the next problem. The next problem is which of the following statements is correct? ZPP is contained in BPP, but we don't know if ZPP equals BPP. BPP is contained in ZPP, but we don't know if BPP equals ZPP. Neither of them is contained in the other, and they are disjoint classes. So which of this is correct? The answer is just here. Yeah, the answer is here. So ZPP is contained in BPP, but we don't know if they are equal. So even that's an open problem. So is this fine? Okay, yeah.
Yes, yes.
Yeah, so then let's look at the next problem. Yeah, so the next problem is the Baker-Hill-Soloway theorem constructs two oracles A and B such that P to the A is equal to NP to the A and P to the B is not equals to NP to the B. And which of the following is correct? Both A and B are explicitly constructed. Oracle A has an explicit construction, but Oracle B does not. Oracle B has an explicit construction, but Oracle A does not, and neither A nor B is an explicit construction. So if you remember the proof, which of these is correct? Okay, so do you remember what A was? Okay, yeah. Okay, so A is correct. Okay, so the Oracle A was explicitly constructed, but because it was just some language which was from a very large class, right? So you could have taken some language which was P space complete or some language which was X complete, and P to the A would be equal to NP to the A. So A was explicitly constructed, but what about B? So do you remember how B was constructed? Okay, so yeah, it was constructed using diagonalization, and so it was constructed in stages, right? But like at the end of the procedure, did we ever get an explicit uh, description of B? We didn't get an explicit description of B, right? Yeah, so A was constructed explicitly, but not B.
So what does it mean by explicit construction?
So generally, explicit construction means something like this. You can tell me exactly what it was. For example, A was some language which was which was X complete or P space complete, right? On the other hand, B depended on how all the polynomial time Turing machines behaved, right?
Yes.
So unless you explicitly like sit down and characterize how all of them behave, you don't have an explicit description of me, right?
Yes. So
Yeah.
how is such a language even usable, like in proofs of like
Okay.
we can say that.
Usable in what sense?
So what I mean to say, like, how can we even use such a language to like uh, keep it as a premise for proving something else? Like the language itself maybe does not exist, or maybe.
Okay, no, no, no. So what the proof proved was that a language exists, right?
Okay. So can we take this question at last because we have issue? I have some doubts in diagonalization. That second part of the proof itself.
Okay, okay.
So
Okay, so there was one more question. Okay, you have, okay, yeah, so BPP versus P is an open problem. So you had a
isn't
question about
P a
that?
subset of BPP?
Yeah, so P is a subset of PPP. What we don't know, so by BPP versus P, I mean, is P a strict subset of PPP
Okay.
or is P equal to BPP? So just like P versus NP problem. We know
Yeah,
P is in
but
NP.
like for the other two, we don't even know if they are subset of each other or not.
Yes, yeah.
Right. So these two, these three, like first two and the last one are different types of open problem
Yeah, so they
instructions.
are of different kind. Yes.
Yes. Okay.
Yeah. Okay, so yeah, okay, so now let's look at the last problem of this assignment. And the problem is which of the following oracle for which of the following oracles A can we say that P to the A equals NP to the A and select all the correct answers? 2 SAT, 3 SAT, TQBF, and M X 1 to the N so that M accepts X within 2 to the N steps. So which of these is correct? Okay, why B? Okay, so there are two answers B and C and D. So the correct answer is C and D. But why did you say that B is correct?
Yes, so I said B correct because I interpreted this question as that when this P A becomes same as NPA.
Yeah, that is
So
the question.
if I have an access to the oracle of the three set, then I would be able to solve three set in one go.
Okay,
So which will make this
which would imply this, right? P
it
to
will
the
make
A
this PA
contains NP.
contains in NP. Yes.
Okay, in fact, it would
Yes,
mean
yes,
this equals to NP.
yes, yes.
But in the
Yeah.
question, we have NP to the A, right?
Mhm. So what if I have I have an oracle for the TQBF? How will it make this PA same as the NP of A?
Okay, yeah, so that I'll prove. But okay, do you see why 3 sat won't work? Because in fact, NP to the 3 sat, okay, what is this NP to the 3 sat? This we have seen what this is. So which
I think
class
it
is
is
this NP to the
sigma
3 sat?
2. It is
Yeah, this
sigma
is
2.
sigma 2. So this is just NP to the NP, right?
Right?
Yes, sigma 2.
Yeah, so if 3 sat were the answer, then it would solve the problem of pH collapse, right? Which is an open problem. So
Right.
as of now, we can't say that 3 sat would work. What about 2 sat?
Two set is for polynomial, so will not make much difference.
Yeah. So 2 sat is in P. So even if so P to the A would be equal to P and NP to the A would also be equal to NP. So 2 sat won't work unless P equals NP.
Yes.
Yeah. And now, okay, so
Okay,
we need to prove.
one
Yeah.
one thing for the 3 sat one.
Yeah.
I think PA is a subset of NPA. This containment would work.
Yeah, that
Right.
would work.
If you look at the reverse one, NPA should be contained in PA,
Right.
which we would need to prove, right? So
Yes.
how would we go about this? Like we have an NP, a language like there is non-determinism, and
Mhm.
for like how are we going to simulate? Like there may be oracle calls while it runs, like in the path there may be extra oracle calls. So
Okay.
when A was so powerful that it could solve it in linear time, so we handled that. Like, how would that explanation work with this? Where would
For
it break? I mean to say,
for 3 sat or DQBS?
for 3 sat, like if 3 sat is the oracle, why would like at what point this proof would break?
Okay. So so for 3 sat we actually know that it's sigma 2, right?
No, no, we know that like that is one way
Okay.
of saying it, but the proof which we like discussed, that was discussed in the lecture for the first part, like PA is equals to NPA. Like, so
Okay.
so in
Okay.
that
So
just a minute, like
okay.
in
So
that, right.
okay. So
Yes, yes,
okay. Yeah. So what you're trying to say is this, right? That just try to do this. You have a non-concept Turing machine which makes Oracle calls
right.
and like replace all of those Oracle calls. Okay, or rather simulate all of those Oracle calls using non-determinism. Is that what you're
Yes,
saying?
yes, exactly right.
Okay. So the exact reason this fails is actually in this proof, right? Because if you remember in this proof, what we did was this, right? That when like basically you were able to simulate the for all quantifier using this oracle access, right? So basically, when you have this oracle, you don't only have an oracle. Okay, so when you have this oracle to 3 sat, you don't only have an oracle for 3 sat, you also have an oracle for 3 sat complement, right?
Yes, yes.
So to to like argue why the proof that you are proposing won't work, consider the following: you have a Turing machine N, which somehow comes up with a formula phi, queries the 3 sat oracle for phi, and then if the oracle says 1, the Turing machine accepts that as 0. And if the oracle says 0, the Turing machine accepts that as 1. Okay. So basically, the Turing machine wanted to query the oracle for 3 sat complement, which is simulated like this. Okay. Is this part fine?
Yes.
Okay. So the point I'm trying to make is NP to the 3 sat can make oracle queries to a co-NP complete problem, right? Now, what you were proposing was this. Let us simulate the oracle of 3 sat using non-determinism, right? But that would only let us simulate queries to 3 sat, right? Not queries to 3 sat complement, unless NP were equal to co-NP.
So in case of Oracle, it doesn't matter whether you are using the Oracle for A or for the
Hmm.
complement of A. This we discussed in the
Right.
last.
Yes. Yeah. And so the problem with using non-determinism to simulate an oracle for 3 sat is you cannot simulate an oracle for 3 sat complement. And it's there where the proof fails. Is this fine?
Okay, I'll go through it again, and if there is
Yeah.
something, I'll get it to it in the next session.
Okay. Okay. And so now we need to prove that C and D work. Okay. So what I'll do is I'll just show that C works. The proof for D is similar. Okay. Okay. So the proof is this. Let L be in NP to the A and there exists a polynomial time.
Hey guys, I'm Nisha Homi. Today I'm sharing a healthy peanut laddu with just three
Okay,
ingredients:
can you, yeah, mm,
oil, refined sugar.
there
Easy to
exists a
make at home
polytime
and
NDTM.
make healthy peanut laddu. To my small chutney grinder,
Yeah,
measuring in about
Six, one of you is not on mute and there is some background. No.
Once the cardamoms are crushed, peel off the skin.
Yeah. Okay, yeah. So there exists a polytime entity N. Okay, polytime oracle entity N to the A, which decides L. Okay. So now consider uh, polytime. Okay. Uh, non-deterministic Turing machine N prime, which has the following. Uh, it simulates M. Sorry, N to the A. Whenever the an Oracle query for a fully quantified Boolean formula, say psi, uh, n prime holds, or rather I should say pauses the simulation of n, uh, determines if psi is in A in polyspace, and then resumes the simulation of n to the A using the answer. Okay, so here I'm proposing a Turing machine n prime. First of all, are you convinced that this n prime correctly simulates n to the A? Okay, so let me ask this question. So in the discussion that we just had, I said that if I had given you an oracle of 3 sat, you could not have done something like this. So in this question, why are we able to, in this uh, situation, why are we able to simulate an oracle for TQBF, but we were not able to simulate an oracle for 3 sat? So why is that the case? Okay, so over there, the reason was that we were trying to simulate the oracle of for 3 sat and therefore 3 sat complement as well using non-determinism in polynomial time, right? Which we cannot do unless QNT and NP are the same. Here we are trying to simulate an oracle for TQBF and therefore also TQBF complement in P space, but both of them are in P space, so we can do this. Okay, is this fine?
Yes.
So this is fine. Okay, okay, so and are you convinced that n prime correctly simulates n to the A? Okay, yeah.
Yes.
Yeah, so okay, so uh, n prime is is an NDTM that runs in. So n prime doesn't polynomial space. Why? Because n prime uh, has to like simulate n and answer all of his queries. Now the simulation of n would only take poly space. In fact, it would only take poly time because n is a polytime machine, right? However, these queries you might need extra space for these queries. For each query, you would need at most poly space because PQBF is in P space. And across queries, you can reuse space, right? So you only need to use at most poly space, poly extra space uh, to answer all the Oracle queries. Okay. So the total space users is still poly. And this means that L is in n space, which is the same as P space. So is this fine? Yeah.
Yes.
Now P space is contained in P to the A. So is this clear why this is true? Okay, yeah. Because yeah, if I like take any language in P space, it reduces to DQBF. So if I can somehow solve DQBF using P to the A, I'm done. So all any Turing machine has to do is to just simply query A on its input and it's done. Okay. And this implies that uh, NP to the A is contained in P to the A. P to the A is contained in NP to the A. So P to the A equals NP to the A. Yeah. So is it clear why this is true?
Yes, because of that theorem, that Leibniz theorems, or what? If I mean, if
Okay. Oh, you don't need any theorem for this. P is contained in NP, right?
yes, yes. So therefore, if I use any oracle, clearly
Yeah.
that relation would be maintained.
Yeah. So basically, for any language in P2TA, you would have a deterministic Turing machine using an oracle, but
Yes,
a deterministic Turing machine is also a non-deterministic Turing machine, right?
yes, yes.
Yeah. So that tells you that it's contained. Yeah. So both are the same. So is this fine? Is this proof fine? Okay. Yeah. So now, so this was all for last year's week 5 assignment. Now what we'll do is we'll take a brief look at diagonalization as we discussed in the last class. And if after this we have time, I'm not sure we would, but if we still have time, then we'll look at this year's week 4 assignment. So is this fine or like do anyone if you have some doubt in this year's week 4 assignment? Okay, yeah. So if you don't have a doubt in this year's week 4 assignment, we can directly look at diagonalization. Okay. Okay, so what I'll do is I'll first show you how using diagonalization. Okay, first I'll show you how you can prove that the set of integers has a okay, the set of natural numbers is a strictly smaller size than the set of real numbers. And I then tell you why that technique was called diagonalization. And then we'll see how that technique was applied to computer science. Okay, so the result that uh, n is strictly n has strictly smaller n is strictly smaller size then R is a result in math, right? So the technique was introduced in set theory, but then it was also used in CS. So first, let me tell you about that set theoretic result. Okay, so yeah, let S and we say that they have the same cardinality, denoted if there exists one-to-one correspondence. Okay, yeah. So, like since N and R are both infinite sets, we can't exactly talk about their sizes. So when we are talking about finite sets, we can use their sizes. But when we are talking about sets which can be finite or infinite, we talk about the cardinality. And so we say that two sets have the same cardinality if there is a one-to-one correspondence between them. That is, there is a one-to-one onto function from one set to the other. Okay. And because of this reason, the notion of cardinality coincides with the notion of size for finite sets. Why? Because consider any finite set. If it has size n, then there is a one-to-one correspondence between the set 1, 2, 3 up to n and that set, right? So you can say that that set has size n. So is this like relationship between cardinality and size clear?
Just repeat the statements once.
Okay, yeah. So suppose you have a finite set with a size n. Okay, then that set you can just number the elements in. Sorry, you can just order the elements in that set as S1, S2 up to Sn. And then there's a natural one-to-one correspondence between the set 1, 2, 3 up to n and S1 to Sn, right? Map 1 to S1, 2 to S2, and so on. And then, so basically, this way of defining cardinality by using one-to-one correspondence is sort of
So can you
is backward compatible to the size to the notion of size.
can you write down this discussion here, because
Okay.
because yeah, it is
Yeah,
it
okay.
is not clearly audible. Yeah, what did you say?
Yeah, so this is what I was saying. And because of this, I can say that S and T have the same cardinality. So what I wanted to say is the notion of cardinality is backwards compatible to size because if the two sets are finite and they have the same size, then they also have the same cardinality and vice versa. Okay. So now that we have this definition of cardinality, let me get to the claim that I want to prove. Is not the same as the cardinality of the set 0, 1. So in fact, the claim is okay. We can show something more. We can show that the cardinality of n is strictly less than the cardinality of the set 0, 1. But I'm not saying that because over here, all I have defined is when two sets have the same cardinality. I haven't defined when one set is a strictly smaller cardinality than the other. Okay. So yeah, let's just not get into that. Just let's look at this weaker version of the claim. The claim that is true is actually this. Okay. Yeah. So and we'll prove this by contradiction. So suppose cardinality of n were exactly equals to n, there must exist. Okay, why are my characters breaking? Let's see how much pattern is there. Is there any pattern from S to T, right? Why? Because this is okay. There is no S, there is no T. Why? Because this is just a definition of cardinal. This is just a definition. Okay, this is just how we have defined two sets having the same cardinality, right? Now, what we'll
Yes,
do is,
yes.
yeah. So now what we'll do is, since every number, okay, for every I, right, f of I. Now f of I is going to be a member of 0, 1. So I can write it in this decimal expansion. So write f of I as a decimal 0.A1 AI1 AI2. In fact, okay, let me, yeah, that's fine. Yeah. AI1, AI2, AI3, and so on. Okay, so we are going to write f of I as this and then create a new number b. Okay, so b's decimal expansion is this p1, p2, p3, and so on, where bi is ai plus 7. Okay, so uh, we have an infinite list of numbers f1, f2, and so on. And by using the first decimal, the digit in the first decimal place of f1, the digit in the second decimal place of second place after decimal of f2, and so on, they are creating a new number b. And now the claim is uh, for all okay, there does not exist Okay, first, even before that, B is clearly in 0, comma 1, right? Because it's 0 point something.
So what's the meaning of this bi is equal to aii plus 7?
Okay, so B is, so I'm writing B in its decimal expansion. It's 0 point B1, B2, B3, and so on. So
Yes,
Bi is going to be a number between 0 to 9, right?
yes.
Okay. Now I also wrote Fi in its decimal expansion as 0 point AI1, AI2, AI3, and so on. So,
Uh-huh.
okay, I should, okay, right, you are right. I should have put mod 10. Yeah,
Yes,
yeah.
yes, it's fine now. And instead of 7, it could be any other number. Is
Except
this
1.
except 1?
Yeah, and the reason is 0.999999 is 1.
Yes.
So basically, if you take 1, then yeah, you need to argue more carefully. It won't work. Yeah. So, okay, yeah. So now AII is it between 0 and 9. So AI plus 7 mod 10 is also digit between 0 and 9. So it's fine, right?
Yes.
Yeah. So B makes sense and B is in 0, 1. So now the claim is there does not exist any I in N such that f of I equals B. So do you see why? Yeah. So if f of I equals B, then 0.AI1, AI2, AI3, and so on is the same as 0.B1, B2, B3, and so on. In particular, uh, AII is equal to BI, which is equal to AII plus 7 upon connection, 7 mod 10. Yeah, so is it clear why there does not exist any I such that Fi equals B? This is the crucial part of the argument.
Uh, yes, but then if you can explain this proof starting from the creation of a new number p again, that would be really helpful.
Okay, okay, yeah. So starting from here, right?
Yes.
Okay, so even before that, we are going to write every Fi in its decimal expansion, and we would need this decimal expansion. So we want to create a new number B, as and we want it to be between 0 and 1, and we are going to create it. In fact, we are going to create it by creating its decimal expansion. Okay, so let these decimal expansion be 0 point B1, B2, B3, and so on, where Bi is AII plus 7 mod 10. Okay, is it clear why this makes sense?
In fact, it is not clear. See, AII is what? I mean, is the I mean, so we are looking for the correspondence of the ith number in the set of the natural numbers. So this AII is the ith term
No, no,
in
no, no,
this
no, no.
expansion.
Okay, so the IR term is Fi.
Uh-huh.
And what is AII? So I wrote Fi as this, right? So
Yes.
I wrote as 0 point AI1, AI2, AI3, and so on. So
Uh-huh.
AII is the ith digit after the decimal point in Fi.
Yes. Yes. And why are we adding 7 into it?
So we don't want Bi to be equal to AI.
Uh-huh.
And the reason for that would be clear over here. So okay, at least till now, does Bi could, okay, are you convinced that Bi is well defined and it's between 0 and 9?
Yes.
Okay, so then if Bi is between 0 and 9, then B is a valid number between 0 and 1, right?
Mm-hmm.
So now what we want to show is that Fi, so there does not exist any I so that Fi equals B.
Mm-hmm.
And the way we are doing it is, if Fi, by contradiction, if Fi were B, then
Mm-hmm.
Fi's decimal expansion and B's decimal expansion must be the same,
Yes. Yes.
which means that the ith numbers after decimal must also be the same, which
Yes.
means,
Should be same, but this cannot happen. Yeah.
right. So at least this claim is clear, right? That
Mm-hmm.
there does not exist any I that Fi equals B. Is it clear?
Your video got freezed, so I could not
Okay,
hear
so what I was asking is
the
it is
last few
this claim,
seconds of your
yeah,
discussion.
is this claim clear? Or is the proof of this claim clear? I in N, so that Fi, there does not exist any I in N, so that Fi equals B.
Yes, it's true. I
Okay,
agree with this contradiction.
okay. So now, but okay, but why did we prove this? So what what are we going to do using this is the following. So f is not an onto function, or other, why should I put this? F is not onto. Yeah, so okay, so from here I want to claim that f is not onto. Is it clear why?
Yes, because yeah, because I is getting mapped to more than one value. So
No, 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 no. I is not getting mapped to more than one values. I is only getting mapped to one value, fi.
mm-hmm.
But we have shown that there exists a b in 0, 1,
Mm-hmm.
which does not have any I that maps to it, right? So
Yes,
there is an element in the codomain which does not have any pre-image.
yes, yes,
So it is not in the range. Since
yes.
so codomain strictly contains the range and therefore f cannot be onto.
Mhm.
And this is okay, so f is not onto, i.e. it's not a one-to-one correspondence. Yeah, because a one-to-one correspondence is just a one-one onto function. We have showed it's not onto, so it can't be one-to-one correspondence, right? Okay, and this is a contradiction, right? Because what was our assumption? We assumed that there exists a one-to-one correspondence from n to 0, 1, right?
Yes,
So this contradicts that assumption, and reason we were able to make that assumption is because of this assumption, right?
yes.
So this proves that so is not equals to, yeah. Is this fine?
Yes. So, but where is, I mean, so I mean, where is the, I mean, how do we use the term diagonalization here?
Yeah, I'm drawing that picture now.
Okay.
Yeah. Okay. So okay, let me hope I can draw it properly. Hmm, this is yeah. Okay, so what I'm going to do is over here, I'm going to write I. Over here, I'm going to write Fi, but in its like decimal expansion. Okay, so this is going to be AI1, AI2, AI3, okay, and so on, right? Let me just write some expansion. Okay, so over here it's A11, A12, 3, and so on. Okay, so what I've written is over here I've written the numbers, and over here I've written, so these are I and these are Fi, but in their decimal expansion. Okay. Now, in the proof, what we did was the following: we used these numbers. I should say these digits. So we used these digits to create a new number, right? So what we did was this. To yeah, and it's because of this reason that this technique was called diagonalization.
Yes.
Yeah.
So from this table, how did we reach to the contradiction then? It's okay that we took the
Hmm.
elements from the diagonal side, it's
Okay,
fine.
no, no, no. From this table, we do not reach a contradiction.
Hmm.
This table is just a visualization of how we created B.
Yes, it is clear now that I mean
Right.
from where are we getting this term diagonalization?
Yes. Yeah. Okay, so if this is clear, now let's look at the use of diagonalization to prove that the halting language is semi-decidable. Okay.
Okay.
Yeah. So, but yeah, before that, is this like completely clear? Because if we move to that and this is not clear, that would be a problem.
It's clear that we are using the diagonal terms here, but then
Yeah.
how are we constructing a new element by adding say 7 in all these terms and taking its modulo with 10,
Right.
and that result into something which is not the image of any element of the set of the natural numbers, right? So I mean, how can we depict this thing from this table? Can we
Okay.
can we
So,
do it?
I mean, okay,
Uh,
what you can do
may I
is,
just
yeah,
say one thing here? Like adding 7 to AI is just in an essence doing that key. We are trying to get a digit which is different that than AI. The higher digit of BI
right.
for the number B. Suppose like we are trying to create B, right? And if we want it to be different from all the numbers in this list. So what we are trying to
Yes.
do that B differs from the image of one at first digit, B differs
Right.
from the image of two at the second digit, and so on. So in
Yeah.
collection, B doesn't match any of these. And even this, if like the set of natural numbers is infinite, since we have mapped each one of them to a number, the such created B would not have like a pre-image. So
Yes. Yeah.
that is essentially what is like plus
Yeah.
7 is not important, but the digit being different than AII is like important here.
Okay.
I
It's
think.
slightly different. Like you can't add just one.
No, I'm not saying add just one or do anything strict. I'm just saying that the digit in BI at particular position, it should be different than what is in like AII at
Yeah.
that
Yeah. So
place.
what I'm saying is, that different. Okay, so there is a slight technicality that on which I did not go into this proof, and that was the following. So to make BI different than AII, you couldn't just say that BI is consistently AII plus one mod 7
No,
mod
I'm not
10.
saying
That
plus.
won't work.
Like we can simply say that if it is 0, where you do it 1, otherwise it is 0.
Okay,
Like
that would still work. Yeah.
it is a textbook proof. Like I think it was in schools or something. Diagonalization has been taught, I think. So it is given like that. So what I mean to say that adding something or doing something is just a way of ensuring that the digit is different.
Yes. But yeah, I mean, even while doing that, you have to be careful that the the change.
Must occur.
Yeah.
Right.
For example, like adding one is a bad change.
Right. It may
Yeah.
happen that there is no change in the digit. Right?
Yeah, because like 0.99999 is just one.
So then we could have add only this 7 only to A11. Why to add this 7 to the other elements of the dynamical
Okay,
side? That
so
will
if
also
you
make.
only added 7 to A11, what would B10 be? The 10th digit of in the decimal expansion of B.
Could not hear your question.
Okay, so suppose you only add 7 to A11, then
Uh,
what would B10 be? The 10th digit in the expansion of B. Are you saying that it should be A10, A1010?
okay. Say 8 and 10.
Okay, but then all you can argue is that B differs from F1, right? How would you argue that B differs from F10?
Mhm. Okay. So B differs from F10, say at the
So,
10th place.
right. Yeah,
Yes.
because we added 7 or because we changed the AII somehow. Okay,
Yes.
yeah. So all of these are like changes are necessary.
Yes, it's yeah. I,
Yeah,
I I understood this. Yeah,
yeah.
fine.
Okay, yeah. So then let's look at diagonalization in the halting problem. Yeah, we would need a few things before we can start. So like encoding the function uh, encodes Turing machines into. So I'm going to assume that the alphabet is 0, 1 star. And so we are going to need an encoding. I'll call it ENC that encodes Turing machines into 0, 1 star. And it's possible to create an ENC which is computable and every y in 0, 1 star is the encoding of at most 1 TM. Okay, uh, let me say exactly. Okay, so okay, I won't tell you how this is. You can do like you can create an encoding which is computable. But okay, one very simple way of doing it is the following. So Turing machine is just a tuple. Write down that entire tuple in the standard mathematical notation, the way we do it on paper, and then convert each and every symbol out in that tuple to a string using either ASCII or Unicode, and that would give you a string which is an encoding. Okay, so is that fine? It's also easy to see that if you do it like this, the function is computable. So till this much is fine, right? So we have an encoding which is computable. We need to show argue that every y in 0, comma 1 star is the encoding of exactly 1 tm. So it's clear that if we do it in the way I've just said, every y in 0, comma 1 star is the encoding of at most 1 tm, right? Now, we want to convert that at most to exactly, and the way to do it is the following. Suppose there exists a y in 0, comma 1 star, which is not the encoding of any tm. Okay, then just say that it is going to be an encoding of some fixed tm m0. Okay, so basically, if something has no pre-image, I'm assigning it an arbitrary but fixed pre-image. So is this fine?
How does that work? Like, I'm trying to relate it with the last proof, where Turing
No, no,
machine
no,
is
no. Okay, so
exactly
okay,
matching.
encoding has nothing to do with last proof.
Okay.
So you just basically find anything in 0, comma 1 star. It does not have a uh, it does not have a Turing machine that it encodes. Just say okay, it encodes some trivial Turing machine. So basically, what I'm doing is that I first created an encoding n prime in the way I just mentioned. Write down the description of the Turing machine, convert it to Unicode. Then I saw that okay, this encoding does not have this property that it like every string encodes exactly 1 tm, but it does have the property that every string encodes at most 1 tm. So I created a new encoding ENC by modifying ENC prime as follows. If a y under ENC prime does not have any Turing machine, say that uh, under ENC, its Turing machine is some fixed Turing machine M0. Okay, is this fine?
So does this mean that there are problems which are beyond Turing machines, because we would be having many strings possible with the combination of 0 comma 1, and however all those strings may not have corresponding TMs. So we do have solutions for the limited problems, and all the problems are not solvable by the Turing machines.
Okay. Can you repeat that?
So we can have a large number of the possibilities. For this y. So many y's are possible, and for every y we cannot have a Turing machine.
Okay.
If we consider a y as a problem,
No,
and
no, no. Why you cannot consider y as a problem? You can consider y as a string.
so yes, so in this case probably we are considering y as a valid encoding, or y is a encoding, or I mean, consider y as a simple string comprising of zeros and ones.
Okay.
So in that case, because y would be there, there would be many y's, and corresponding to every y, we cannot have a Turing machine. I mean,
Why?
can we have a Turing machine corresponding to every y? So consider y as a description of a problem,
Okay.
and
Where is
consider.
problem coming from?
So problem is coming from, say, if we try to, so let us fix to this notion that an algorithm is what Turing machine realizes.
Okay,
So
fine.
fine. So consider, say, y is a collection of say all possible problems, right? For
Okay, no,
which
no, no.
we have,
Y is just 0, comma 1 star, right? So y is
yes,
just an element of 0, comma 1 star. It's just a string.
because it is a string, yeah. So we so think of the y as the collection of many problems. I mean, many strings, many
No, no,
binary
no, no.
strings.
Okay. First of all, a problem is going to be an infinite set, right?
So problem is not the infinite. Problem is language is the infinite set, right?
Okay, so what do you mean by a problem?
So problem is a string, right? So an instance of the problem, an instance of a language. So if we are, yeah, it's true that the problem is the language is the problem, but
Hmm.
I mean to say here that y is a problem instance, say, or
Okay.
yeah. So I mean that if we have been given many instances, probably the discussion has probably moved to a different direction. But I just wanted to say that if y is, if we consider a binary string as a problem formulation, right,
Okay.
and then we are having many problems,
But
and
why can't we have many Turing machines?
and then y can have many, and then corresponding to that problem, I mean, there is a sequence of the zeros and ones getting mapped to the another sequence of the zeros and ones, and in that another set of or another sequence of the zeros and the ones, we have the description of the or the encoding of the Turing machines. Let us consider a mapping from the set A to the set B, and
Okay,
A
what is
compares.
A, what is B over here?
Okay, so B is the set of all the encodings of the Turing machines possible, valid encodings of the Turing machines.
Under some encoding scheme, right?
Yes. And say
Okay.
A is a set of all the problems possible, all the
Okay, what
problems
do you
which
mean
can.
by problems?
So yeah, so because if I want to define any problem, then clearly I would be describing its description through a binary string only.
Okay, no, 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 no. So, okay, what do you mean by a problem? Is it a is it a language or a problem instance?
Okay, so here the problem is a language. Yes, you're right.
Okay,
The
right.
problem
But
is a
the
language.
language contains infinitely many strings, right?
Yes, yes, true.
So, okay, if you are thinking of this, take all the strings, put commas between them, that won't work. Why? Because every member of 0, comma 1 star is a finite element, right?
Yes. So here, since y is, I mean, y is infinite as such. This is a
No,
clean,
no, y is
cleanly.
finite.
Y is not finite here. Say, let us
Y
let us
is
let
finite. No, 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 no. This set is infinite.
this set is
But
infinite. Yes.
okay, so
So
what
let
is
us
this set?
so yes. So instead of viewing this y as an element of the cleaning closure of 0, comma 1, view it as say y is equal to the cleaning closure of 0, comma 1.
No, 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 no. Okay. So, but y, okay, so y is a string, right?
Y is a string, and you view it, say this is string. This since the length of this string is infinite,
No, no, no,
right?
okay, okay. A string can never have an infinite length. Here's
Yes.
why.
So yeah, true. So
Right.
the length of the string cannot be infinite because the
Hmm.
cardinality of the language is infinite, wherein the length of each string is finite. That's true.
Okay.
Language is the collection of the infinite strings,
Right.
wherein the
Okay,
length
length
of
is a
every
connection of finite
length,
strings. Language is
yes,
an infinite connection of finite strings.
finite strings, right? So the length of every string is finite. So now I mean
Yes.
to say here is that if you view this y as an infinite collection of the zeros and the ones.
Okay, no, but how can I view that when y is a string?
Okay, so instead of viewing y as a string, it was just a thought that if you view y as a collection of, say, all the problems, say y is the collection of all the
Okay, okay, but
languages.
then what you are doing is you are saying, let's map a Turing machine to a language, okay?
Yes.
So then you no longer have an encoding, right?
Yes. So for I mean, we have languages. Say language is the I mean, obviously it would be comprising infinite set of the zeros and ones. So this
Hmm.
L. So if I view this y as the as infinite set,
Okay, so
right?
why? Okay, first of all, by viewing y as an infinite set, what you are telling me is I'm instead of encoding from Turing machines to 0, 1 star, let me encode from Turing machine to set of languages. Okay, is that what you are saying?
Yes. 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 Yes.
Okay,
So there would be many languages for which the construction of the Turing machine won't be
okay.
possible.
Why? So you are saying that there would be many languages, but why can there be many Turing machines? So we need to show that the cardinality of the set of languages is more than the cardinality of the set of Turing machines, right?
Oh, that will always be the case because of the recursively and I mean
No, no,
because
no, no,
there,
no, 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 no. Okay, okay, okay.
yeah.
Look at the heading. We are going to use diagonalization to show that halting problem is undecidable, semi-decidable, right? A priori, we have no reason to believe that there exists a problem which is not recursive, right? Do you see the problem?
Yes, yes, fine.
So right now we are at the stage where we have defined recursive, we have defined recursively enumerable, but we haven't proved that there exists a language in recursively enumerable which is not recursive, right? That is what we are trying to prove, right? Because that when we prove that halt is semi-decidable, we would have shown that there exists a language which is recursively enumerable but not recursive. That's what we would have done, right?
Yes, yes,
So
yes.
basically, what I'm saying is, you are right. There are many more languages compared to Turing machines, but from here you cannot say that. That's what we have to prove. Okay.
Okay, now I understood you.
Yeah. Yeah.
Clear. Fine.
Okay. Yes. That was okay. Yeah. So we have this encoding with these properties. It's computable. Every Y maps encodes exactly 1 TM. Okay. And what I'll do is denote by n inverse Y this TM. Okay, this is just so far I've just set up notation. I haven't like gotten the proof yet. So the proof starts now. So first let me quickly define the languages. So halt is this y comma x such that n inverse y halts on x. Okay, so we want to prove that this is semi-decidable. And to do that, we would use these two languages, not self-accepting, which is just y, such that n inverse y does not accept y. And what do I mean by it does not accept y? It either rejects y or on input y it never halts. Both of them mean that y is not accepted, okay? And self-accepting is y such that ENC inverse y accepts y. So now observe that self-accepting is just, oh, so okay, I'm over here. Okay, let me write it like this because I haven't defined what a universal set is over here. So this symbol means a disjoint union. So like two sets are disjoint and I am taking the union. And I'll call this set 0, comma 1 star as a universal set. So uh, self-accepting is the complement of not self-accepting. Is this fine? Okay, are the three definitions and this line fine? Okay, yeah. Okay, so now uh, what will what I'll first do is this. Okay, so the strategy we are going to follow is this. We are going to show that this language is undecidable. That would somehow imply that this language is semi-decidable. And we are going to argue that this language reduces to this language. And so this language can be at most semi-decidable. Okay. So let me do the third step first. Hmm, which number is this? 3. Okay. Even before that, let me just write what I said. That would make the proof much more sensible. Because the set of recursive languages their complement. Okay, so is this claim clear that if NSA is undecidable, then SA cannot be recursive?
Could you just like brief why?
Okay, so suppose SA were recursive. Okay, then what does that mean? If so, SA has a halting Turing machine deciding it, right? So take a string y. Okay, so you want to. Okay, what I'm going to do is using a halting Turing machine M for SA. I'm going to consider a Turing machine M prime for NSA as follows. Given a string y, I will feed y to M, check if it accepts. If it accepts, I'm going to just flip it. So basically, if you have a deterministic Turing machine deciding a language, you can use that to construct a deterministic Turing machine deciding the complement of that language, right?
Yes, yes.
So if NS is undecidable, there is no Turing machine that decides NSA, right? That means that there cannot be a Turing machine that decides SA. Okay.
So like flipping the output, isn't it that like what we used the diagonalization to prove in the other theorems, like creating a Turing machine which flips the output of another Turing machine?
I mean, sure, flipping is a common operation,
Right.
but okay, so it depends on which context you're using it, right? For example, to prove that P equals copy, you would use a similar flipping, right? To the one I am talking about over here. So just
Okay,
because
so
you
yes, yes, I got it. Like we use the same notion, like flipping the output various to prove various things.
right, yeah. Okay, so this means that SA cannot be recursive. In fact, this implies SA is semi-decided.
So in case of semi-decidability, we would be having the answer of yes and unsure of no.
Yes, yeah.
Okay.
And why is this the case? Because there is an algorithm that can always accept valid instances of SA. What do you do? Uh, Given y, figure out this thing and just run this Turing machine on y, and if it going to accept, it's going to halt and accept, right?
Yes, yes.
So if we show that SA is not recursive, we would have shown that SA is semi-decidable. Okay.
Yeah.
And the claim is if SA is semi-decidable, so is halt. Okay. Can someone tell me why this is true? Hint is reductions. So hint is this. SA reduces to halt. In fact, this
Yes.
reduction is polytype, but don't worry about polytype.
Uh, yes, it's true because yeah. So
So an instance of SA is Y, right? How should I create an instance of halt? For that, I need two things, Y and X. So what is Y? What is X?
yes, so y is the encoding of the Turing machine and x is the input.
Okay. Yeah, that is what's Y going to be in the definition of halt. But given an instance Y of SA, how would I create an instance Y of halt? So given Y, what should I write in place of Y over here? What should I write in place of X over here?
So S is nothing but y comma y. So
Almost. Where Y prime is the encoding the TM obtained from int inverse Y by modifying it to uh, go into an infinite loop when it rejects.
So in case you are writing something on this, then yes, visible now, visible.
Yeah.
Fine.
Yeah, so we need to modify y a bit because, okay, y can halt in two ways, right? It can accept and halt and reject and halt. So just because y halts, sorry, just because the n inverse y halts does not mean that it has accepted y. It could have halted I in the reject state, right? So what we are going to do is take that machine, put a self loop on the reject state. Now it can only halt when it accepts, right?
Yes. So can you say this thing again?
Okay. So we have a Turing machine n inverse y, and
Mm.
we want the following behavior from it. It either accepts y and halts or does not halt at all. But for n inverse y, there are three behaviors. It accepts and halts, rejects and halts, or does not halt, right? So I want to
Yes.
get rid of this reject and halt behavior. So what I'm going to do is, in the I would look at the reject state of n inverse y, set an infinite loop on it with an empty transition. So once it gets into that state, it would do infinitely many transitions from that state to that state.
Yes. Yes. Clear.
Those are meaningless transitions. Yeah. So now there's just two behavior: accept and halt, or never halt at all.
Yes.
And now this is a valid thing for halt, right?
Yeah.
Yeah. So yeah. This okay. So this shows that okay. So since SA reduces to halt, this means that halt can't be recursive, right? Because if halt were decidable, I could have reduced from SA to halt and used the Turing machine for halt, right? Okay, but why is halt semi-decidable? Halt is semi-decidable because, in fact, semi-decidable. Why? Because there is an algorithm for halt, right? Take y, take x, like look at which Turing machine is encoded in y, run x on that Turing machine. If it halts, it halts. If it doesn't matter, right? Because we're only interested in semi-decidability. So is this fine? Why halt is semi-decidable? If it's not decidable?
Yes.
Yeah. Okay, so now is the main part where we are going to use diagonalization, and it's this plane. NSA is undecided. Yeah, so recall that what was our strategy to show that NAC is undecidable. This would imply that SA cannot be recursive. In fact, SA would be semi-decidable. And from this claim, this would imply that halt is semi-decidable. Okay. So if you prove this claim, we are done, right? Okay, so let's look at the proof for this claim. Okay, suppose not. Okay, I like it, I suppose not. So if NAC is not undecidable, that means that there exists a Turing machine M which recognizes NAC. And what do I mean by recognizes? If a string is in NSA and that Turing machine halts and accepts that string, if the string is not in NSA, then the Turing machine might either reject it, re- reject it and halt, or never halt at all. Okay, that is what I mean by recognizes NSA.
Your video got freezed again.
Okay, So by recognizes NSA, what I mean is the following. If a string Y is in NSA, then the Turing machine M on input Y must accept and halt. And if Y is not in NSA, then it can do one of the following. It rejects and halts or never halts at all. Okay. 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 Can you hear me now? Okay. Can you hear me?
Yes, so your video is frequently getting freezed. So can you explain the meaning of, I mean, can you yeah, repeat this thing?
Okay.
Uh,
Yeah. So
that
by
there
re-
exists during, yeah.
okay. So by recognizes NSA, I mean the following. If Y is in NSA, then M accepts and halts. And if Y is not in NSA, then it number one either rejects and halts or uh, never halts at all. Okay,
So if NSA suppose not, then there exists a Turing machine M that decides NSA, not
recognize
reject.
this
Why
because
so?
it's okay. So there are three things, right? Recursive, semi-decidable, and undecidable. So when NSA is undecidable, it is either semi-decidable or recursive, right?
True, true.
And everything that is recursive is also inside semi-decidable, right? So basically, if you have a halting Turing machine that decides a language, that halting Turing machine also recognizes the language, right? So what I'm saying is, if NSA is not undecidable, then either there is a halting Turing machine deciding the language. Okay, so if NSA is undecidable, then there is either a halting Turing machine that decides NSA, or there is a non-halting Turing machine that recognizes NSA. Okay, is this fine?
This is slightly difficult to understand. So, what did you say that if something is undecidable, so either it is
Okay, so if something is undecidable, either it's semi-decidable or decidable, right?
yes.
But in both cases, there would exist a Turing machine that recognizes NSA. Why? Because if you have a Turing machine that decides NSA, it also recognizes NSA, right?
Actually, this is the issue of your video, or probably, I mean, maybe because of some
Okay, so
connection issue.
let me just
That
stop my
at
video.
the right time, or whenever when you make an important statement, this your video gets freezed.
But so can you still hear my audio?
Yeah, yeah. Let the audio go and pause your video.
Yeah, so I've stopped my video. Is my audio still audible, right?
Yeah, yeah.
Yes.
Okay, so now what I was saying is, uh, if you have a Turing machine that decides the language, that Turing machine also recognizes the language, right?
So you went out inaudible again. So that
Okay, so
statement we couldn't hear.
if you have a Turing machine that decides a language, that Turing machine also recognizes the language,
You're
right?
still inaudible, but the icon shows you're speaking something.
Can you repeat that?
You're still on. You were still on it inaudible, but it was showing that you were speaking something. So we couldn't hear what you said.
Okay. Okay. Can you hear me now? Hello. Can you hear me now?
Yes, yes.
Okay. Yeah.
Yes.
Yeah, so what I was saying is, a Turing machine that decides the language also recognizes it, right? Because recognizing is a general notion than deciding, right? Because in recognizing, I'm allowing it to not halt, but that won't even ever occur for for attenuation that does halt, right? Okay, yeah. So is this clear? Okay, yeah. So if NSA is undecidable, then we have a Turing machine that recognizes NSA. Okay. So now, uh, what I'm going to do is let y be any. Say, let's take a graphically first. Or yeah, I don't need. Yeah, any fixed. Okay, yeah, so yeah. So this just means that the language of M is NSA. So by this notation, language of M, what I mean is that the language that M recognizes is NSA. Okay. So now let Y be any encoding of M. Okay, so now there are two options, right? We'll show that Y in NSA and Y not in NSA both lead to a contradiction. So if we show this, then our assumption that there exists a Turing machine must be false, right? Because either a string is in NSA or it's not in NSA. So is it clear that if we show this contradiction, then M cannot exist and NSA is undecidable? So is this clear? Okay, so if this is clear, let's just do this. So first is Y is in NSA. But what does this mean? Y is in LM implies M accepts Y implies N inverse Y accepts Y. Why? Because Y is just the N encoding of M, so N inverse Y is going to be M. So these two statements are exactly the same, which implies Y cannot be in NSA. Okay, so were statements up to here clear? Yeah, so okay. Now let's look at this last implication. Why is that true? So Y, okay, so NSA is a set of all language, set of all strings Y, so that N inverse Y does not accept Y, right? So if N inverse Y accepts Y cannot be in NSA, right? So is this fine?
Yes.
Yeah. And this is the contradiction, right? Because we started off with Y in NSA, got to Y not in NSA, a contradiction.
Yes.
The other case is similar. Yeah, let me write implies over here. So what does this imply? Y not in LM. This implies M does not accept Y, which implies, again, just as before, N inverse Y does not accept Y, which implies Y in NSA. So, okay, I'm seeing some thumbs up. So, are all the implications clear? Your voice broke if you were saying something. So, are all the implications clear, or should I explain some implication?
Yeah.
So, all are clear, right?
Yes.
Okay. So, in both cases, we get a contradiction, which means our assumption that there exists such an M must be false, right?
Yes.
So, NS is undecidable.
Right.
Yeah. Okay. Now, okay, we are way over time, but let me quickly tell you why this is. This is also a diagonalization proof. So, I'll draw a similar table. Okay, so over here we are going to have Turing machines, and over here we are going to have their encodings. M0, okay, yeah, M1, M2, so on. Y0, Y1, Y2, Y. By this I mean, okay, yeah, this, yeah, let me just say. Okay, so we have done a table again. Over here I have all the Turing machines. Over here I have all the encodings. Now, if you look at the proof, what is the proof showing? I have some M over here, right? Can that M be M0? No, because what we have shown is that if M were M0, then it cannot accept Y. So yeah, so if M were M0, then Y0 cannot be in the language of M0, and it must also be in the language of M0, right? So both these are false. So basically, Y0 leads to a contradiction for M0. Is this fine? Similarly, Y1 leads to contradiction for M1, Y2 for M2, and Yi for Mi. So again, we are using the elements on the diagonal to get some sort of a contradiction. Okay. So again, this is called diagonalization. So is this fine?
Yes, but then how to construct something new out of the elements of the diagonalization here?
Okay. So over here, we're not constructing something new. We are using them to prove a contradiction. And okay, we did construct something new, but that was a language NSA. Because okay,
Yes, yes,
if
I got
this
it.
were zero, we would have in NSA we would say this is one, and if this were one, we would say zero, right? So we did construct something, but that was implicit sort of. No, it was rather it wasn't as explicit as in the case of the previous diagonalization argument.
And okay, so these problems are likely to be solved by the diagonalization. I mean, how to find the sum of the ingredients in the problem which indicate.
So your voice broke. I couldn't hear the last part of the statement.
So yeah, so my query is that how to know that whether this problem is, I mean, can be solved using diagonalization. So how to find
Okay,
those?
yeah. So that okay, that question is the same as asking, given a problem, how do I know whether I can solve this using greedy or not? Yeah, there is no general way to say that.
Are there some guidelines? I mean, some elements in the problem which indicate that okay, probably I can try diagonalization here.
Okay, I don't know if there are elements that indicate that you can use diagonalization, but there are certainly elements that indicate that you can't use diagonalization. In particular, Baker-Gill-Soloway theorem tells you that you cannot use diagonalization to solve so that P not equals NP.
Yes, that is there.
Yeah. So in general, like there is no recipe that you can follow to decide whether you should or should not use diagonalization.
Yeah. Okay.
Yeah. But that said, a just one last comment that diagonalization is in Baker-Gill-Soloway theorem is a little more general than this. So in both the diagonalizations that we saw, we were using the diagonals somehow, right?
Mhm.
So in the diagonalization in the okay, so when we say that Baker-Gill-Soloway theorem says that diagonalization cannot be used to prove P not equals NP. What we mean by diagonalization is something more general, and that was covered in class, right? So you would have seen that by diagonalization, we mean that any proof that uses number one, the existence of encodings, and number two, the existence of universal Turing machine. So it's a little more general than that. So if you see over here, we used the fact that encodings exist, right? So even this proof is a diagonalization proof in that sense, but a diagonalization proof in that sense might not be a diagonalization proof in this intuitive sense of playing with a diagonal. Okay, is this fine?
Yes. Yes.
Yeah. Okay. Yeah.
So, like, is the lecture concluded?
So if there are no more questions, we can conclude. Otherwise, if you have a
Uh,
question, yeah.
okay, yes. So just one thing, like, in continuation of this diagonalizations and all,
Right.
there were a few doubts regarding the proof of Baker-Gill-Soloway
Okay.
theorem and the assumptions taken in it. So
Okay.
how are we going to, like, we can't do it today, obviously. So will we start with it in the next lecture, or when can we
Okay.
discuss
Again,
it?
we can do the same thing. So this time we first solved the last week's assignment and then did like this diagonalization. We can do something similar. We can solve last year's assignment, and then once we are done, we can talk about your doubts.
Okay, sure.
Yeah. Okay. So if there are no other questions, we can end the meeting today.
Yeah. Thank you. Thank
Yeah.
you so
Yeah.
much. Good night. Bye. Bye,
Okay.
everyone.
Bye.
Thank you.